Yeah. I know, she's so fun. Okay. So, got your last assignment. Woo-hoo. Don't worry. It's going to be, I'd say, pretty breezy. Because chapter 7 is kind of like a whole new chapter. Well, because we're done with hypothesis testing, we're done with confidence intervals. I mean, we could keep going with them. You can definitely do hypothesis testing and confidence intervals in regression, but we won't be. Okay. So I've got I'll just grab you a photocopy after class, okay? Yeah. Good. Because I feel kind of cheated. I just found out the other day that there's a printer right there, but I've been going upstairs. I should have looked around. Should have done a recce, but whatever. Now I know, and for some reason I feel cheated. But okay, so assignment 6, you handed assignment 6 in. Proportions, I don't know. I think they're a little bit easier than means questions, right? Because there's really only one sample proportion or 2 sample proportions. That's it. Okay. Any questions about chapter 6 before we get into chapter 7? Just do it. As a heads up, once we're done chapter 7, we are going to go back and do the binomial. Remember that day that I couldn't come? We'll have to go back and go over that. Okay. There won't be an assignment because it was on assignment 3, I guess, at the back there. So you can do it on your own. I posted the solutions, but you won't have to hand anything in because, well, I'm not making another one. So, all right. So, just as a note up top here, I'll say after chapter 7, we will go back and cover 3.4, which is the binomial. The constant hump. Okay. So just so you know where we're headed. All right. So, like I said, chapter 7 might be my favorite chapter. It might be because of the placement, right? Because now we're kind of out of the woods, and chapter 7 is probably familiar to, I dare say, all of you. At some point, you've probably drawn a line of best fit, right? So you've made a scatter plot, and what's pretty fun is that in the labs, right, we've had to bump the regression lab, but it's pretty straightforward, right? You're plotting a scatter plot of 2 numerical variables and looking at their relationship and modeling their relationship, and that is regression. Yeah. So regression is just basically fitting lines of best fit. Basically. So, there's a lot of kind of little things that we need to talk about first before we can actually get into fitting the lines of best fit. I have to grab some photocopies of the notes, but I guess that's hard to follow along if you don't have the notes. right there. If you don't have the set of notes, who came in 3 notes? Maybe share with someone next to you. If the person next to you can be kind enough to let you look, and then I'll run grab the photocopies after. Okay, so higher turnout today than I expected. That's good though, I guess. Makes me look not prepared. But look at how many chapter 6 notes I have. Still. So, like I said, there's a couple of things that we need to talk about, just kind of theory stuff that we need to cover that goes into regression. But what you'll find is that the questions that we'll be doing are really straightforward, right? So a line will be fitting straight lines. If you remember, the formula for a straight line is y equals mx plus b. Might sound familiar. For some reason, that's the form that we usually use in high school. So basically just finding the slope, finding the intercept of this line, and using it to predict new values. So the whole point of regression is to be able to predict future values or predict other values, right? So we collect data, and same idea, right? We take the sample information and then we try to infer something about what's happening in the population. So we're going back to scatter plots, right? And we talked about them just briefly, maybe in the first day or the second day of classes, where you've got the y-axis, the x-axis, and let's just say you've got some sort of relationship like this. Whatever your research question is about, that's your response variable. So your response variable goes on your y-axis, and then your explanatory variable goes on the x-axis. First thing you're going to need to do is figure out, okay, which one is my response variable, which one is my explanatory variable. Sometimes it's not going to matter, right? It's just going to be, how do you phrase the question, right? Does the response variable depend on changes in the explanatory variable? And so our research question is going to be do changes in y depend on changes in x? So now we're not doing formal hypothesis testing. We're just, if we have some question like, I don't know, I'm blanking. I'll go to this crutch here. So we've got this example. Later on, I talk about, do ice cream sales depend on the temperature? Yes, right? And so we're expecting to see some sort of relationship. And so when we have a scatter plot, just like when we think back to when we got a histogram, right? There were 3 things we had to talk about: shape, center, and spread. Same idea when we're looking at a scatter plot, which is showing the relationship between 2 variables. Then we have to talk about 3 things. And so we have to look at the form. And so we're looking for just general patterns. Specifically, do they form a straight line, right? Do we have a linear relationship? And you had to do that in the lab, right? Where you said, okay, is a linear model appropriate? Yes or no? We still went ahead and fit a straight line because we're not going to delve into nonlinear relationships. But so for now, because all we will be doing is fitting straight lines, we better make sure that it looks like it follows a straight line pattern, right? And so, so you look at the form, just looking for patterns and visible outliers. If there's no clear, distinct nonlinear relationship, right, like a curve of some sort, then you can probably say it's linear. And so next thing we're going to look at is the strength of the relationship. The strength of the relationship is how close together are these points, right? Are they all really close together and nice and strong, making this strong looking pattern? Or if you've got like random scatter and it doesn't really look like it matters where you would put the line of best fit, right? It can be anywhere in this cloud of dots, then you have a weak relationship. Depending on what field you're in, I mean, for the strength, I've seen fields that divided up into 8 categories. Right? Oh, that would be a moderately strong relationship. Oh no, that's a weak relationship. Anyways, so we're just gonna go either it's strong or it's weak. I'm just gonna keep it that way. And then we're gonna look at the direction of the relationship. Right, so if we've got this kind of upward blowing pattern, then we have a positive relationship. If it's heading downwards, then we've got a negative relationship. Where am I going to put this? Here. Out of room. So if we've got something like this, this is a positive relationship. If we've got something kind of heading downwards, we've got a negative relationship. So same as for histograms, you have to touch on all of these 3 things, right? The form, the strength, and the direction for all the marks. I think I was nice on the assignment. I think I made it worth 3 marks. So you have to touch on all 3, I think. So the example that we're gonna keep coming back to is the relationship between high school grad rates in all 50 US states and DC, and the percentage of residents who live below the poverty line, which is defined as income below $23,050 for a family of 4 in 2012. First thing we're going to do is we're going to describe this relationship between the percent in poverty versus the percentage of high school grads. And so right away, just because I've given you the scatter plot, you know that your y-axis is your response variable and your x-axis is your explanatory variable, right? And so we've got here, we've got your response, and here you've got your explanatory. Okay. Looks like it follows a straight line. Let's see. Okay. Just looking at this, it looks like we've got this linear pattern, no distinct curvature at all, right? And so we can fit a straight line to this. And so I'd say, what would I say? I'd say it's strong-ish. You can see where the different categories for the strength come in handy, but for me, as soon as I'm able to see a distinct pattern, right, then I can call it strong or moderately strong if you want to, right? So looking at this, yeah, we see a trend here, right? And so that's making it strong. It's not super strong, right? But it's still strong. Okay. And so, and heading downwards, right? So we've got this negative relationship. Okay. So you have to be able to describe the relationship between two variables. We're only going to look at two numerical variables. So for regression, you can use a categorical variable as your explanatory variable, but for us, we're just going to have two numerical variables. Oh, or you can make a scatter plot. So there's a scatter plot package in R, and I think it's really fun. So there's some cats, other cats. Instead of dots, it's cats, in case you can't tell. And also, Steve told me that I guess this is a famous cat, Nyan cat. Yes. I had no idea. I just thought it was really cute. But now I know, and I've seen the video. How I missed it, I have no idea, but must have been living under a rock or something. But anyways, I've given you the code in case you want to make a scatter plot for yourself. You can just Google scatter plot. I just stole it from there. You are going to have to install the DevTools package, but then that would be all. And then you can just copy that code and run it and have your very own scatter plots. Anyways, that's not important, but it is really fun. So, I don't know, it gives you this, and I couldn't figure out how to turn it off, so anyways, that's nothing. It's part of the rainbow cat. So there's the multi-cat and the rainbow cat. It's the rainbow cat that's giving me that weird outfit, but it was worth it, I think. So, keep my scatter plots up for a little bit longer.
I'm really glad to know that that's an R.
It was like when they first released the scatter plots package, it was like the whole R community was like, okay, let's get to work, guys. You figure out the shapes, you figure out the colors. And yeah, so there's like so many things that you can do in the scatter plot package. It's really bizarre. Even like hardcores who are like, no, you shouldn't be obscuring the information with unnecessary details, like cats. They're like, yeah, it's pretty fun, it's pretty cool. So, so there's lots of things that you can do. They've added, I think there's 11 shapes. I'm only showing 10 shapes. I only picked well, by default, it just gives the 10 cat types. But I guess there's 11 shapes now, so I wonder what it is. But the laying down, the playing one, the sitting one, lounging one. Anyways. So, bet you wish you had your scatter plots for your regression lab. Turns out, we were playing around with it yesterday. It turns out you can't fit the ab line on a scatter plot. Not sure why, but probably because it's not meant for modeling. But they're like, oh, we don't need that. Okay. But anyways, so key thing, right, is that we're looking for this linear relationship, mostly because in this course, we're not going to learn how to model a nonlinear relationship. So we have to have this linear relationship, but also because it opens up a whole bunch of things that we can do. Right? We can fit a straight line to it. We can model this relationship. We can measure the strength of the relationship and find the direction of the relationship. And we can also measure things like the variability, and most importantly, I would say we can predict future values, right? So not necessarily in the future, but just values that we haven't measured, we can predict. Okay? So I keep saying that we're not going to fit non-linear models, but let's just quickly talk about what would we do if we had a nonlinear relationship, right? Because it can happen. But if you're dealing with a nonlinear relationship and you haven't gone further in stats, should probably just let someone else do it. But what could yield a nonlinear relationship are things like, okay, well, if one of your variables or both are not normally distributed, you're going to have a non-linear relationship. What we do is we transform the data. And so we apply some sort of transformation, often a log transformation. So we use the natural log, not log base 10, doesn't matter, but we use the natural log. And so a lot of the time, I think in some of your data sets, even that you've picked in the lab, right, you've got the ln of income or things like that, right? So some of you have variables that are already logged. Okay? And so once you take the log of something that's non-normal, it can turn into a normal distribution. The hard part with transformations and why we don't just go into it willy-nilly is because when we're interpreting this data, right, we have to think about, okay, well, we're not just interpreting the income, for example. So income is a pretty common non-normal distribution, right, because it's often skewed to the right, right? We've got a cap, and then most people are down at the lower incomes, right? And then there's, you know, the very few with extremely high incomes, right? And so we've got this skewed distribution. So income, money is often non-normal. So then we would have to transform it somehow. Once you've transformed it, it will start to look like a normal distribution. And that's kind of how you pick your transformation. When it starts to follow a normal distribution, then you've done it. Okay? Once you've transformed it though, right, then you will have a linear relationship, and then you can just fit a linear model to that transformed data. Right? But then when you're untangling it and interpreting it, you have to remember your transformation and to kind of undo your transformation. There's my side note. You can set it and forget it. Fine. But now I can say I've talked about it. Great. So, back to important stuff. So just like we had numerical measures of center and spread, right? When we're describing a histogram, we had to talk about the shape, the center, and the spread. And then we said, well, actually, we want more kind of robust measures for the center and spread. Same idea here. We've got a scatter plot. We're talking about, well, is it linear? What's the strength and what's the direction? We've got this numerical measure of the strength and the direction of a relationship, of a linear relationship. Okay? And that is the correlation. Between two provides a numerical measure of the direction and strength of the linear relationship. Just emphasize that. So correlation is denoted by lowercase r or uppercase r. Doesn't matter. I've used lowercase r because that's what I'm used to, but I mean, uppercase r in this case is the same. So just be careful because uppercase r, right, that's the programming language that we're learning in the lab. And so that can get confusing, right? But from context, you'll know which one's which, right? So we'll have to calculate the correlation, which is this nasty bit, technically, right? But what we're gonna do is we're just gonna use this next one here, which means we have to have the S of XY, which is the covariance. We've seen S subscript X, right? That's the sample standard deviation of your X. And then S subscript Y is the sample standard deviation of your Ys. So let's just say here. S subscript X is the sample standard deviation of X, and S subscript Y is the sample standard deviation of Y, of course. And then I've got the formula for SXY, which is the covariance, but I'm just going to give it to you, right? And so I'll give you the two standard deviations as well as the covariance. So SXY is the covariance of X and Y. I will give you S subscript X, S subscript Y, and SXY. But in case you ever have to calculate it, you can find SXY. It's basically like an elaborate standard deviation calculation. Covariance, yeah. Oops. Thank you. Okay. So I'm going to give you SXY, SX, and SY. And from there, you'll have to calculate your correlation, right? But if you have these three numbers, right, calculating the correlation isn't that bad. So the correlation, like we said, is a numerical measure of the strength and the direction of a linear relationship. And so just some key things to keep in mind about the correlation is that it's going to be between -1 and 1, right? And a correlation of 0 is going to be no correlation, right? There's no relationship between these two things. And then as we move out to +1 and -1, then we're going to get a stronger and stronger relationship. And so, of course, moving into the negative end is just telling you that, hey, you've got a negative relationship. The positive end just means you have a positive relationship, right? So it's kind of the mirror symmetric. Right? And so we can do I tried to use as little paper as possible, but now I don't have very much room. Got all these margin things. I'll just put it down here, where if we've got our correlation going between -1 and 1, centered on 0, right, on the negative end, we've got a negative relationship. And on the positive end, we've got a positive relationship, right? That's how it tells us the direction of the relationship. Not that crazy. And then here, somewhere roughly between -0.5 and 0.5. So I'm just drawing the line halfway through. So 0.5 and -0.5. This, if you're down here between the 0.5s, I would call this a weak relationship. And then anything past 0.5 on either end, I'm calling a strong relationship, right? And so, like I said, some fields break it up into 8 parts, right? And so just dicing up this line. But for us, you're welcome to throw in a moderately strong or moderately weak if you want to. But for simplicity, I'm just going strong and weak. Okay. So if we've got this scatter plot again, right, and here's our line of best fit, which we haven't figured out what it is yet, but we can definitely put it on there, right? If we were given these options as our correlation, we can figure out which one is most likely to apply to this scatter plot. And so first things first, well, let's look at these values. Okay, so we've got positive values and negative values. And looking at this here, right, we've got just a negative relationship, a downward relationship. And so these ones are out. A and D are out. Looking at the next ones, one kind of glaring one is the negative 1.5, because the correlation can only be between negative 1 and 1, right? So a negative 1.5 correlation can't happen. Okay. And so that one's out too. And then, given the options between negative 0.1 and negative 0.75, remember what we said, because we can see some pattern here, right, I'm going to call it strong. And so a correlation of negative 0.1, well, that's really in the weak zone here, right? And a correlation of negative 0.1 would just look like random scatter everywhere, right? And so by that, it has to be a correlation of negative 0.75. So that's what I mean. You don't have to have a super, super strong relationship to have a correlation that's pretty high, right? The negative 0.75 on this scale, right, would be pretty high, right? But this is what it would look like in terms of a graph, right? And so that's why I say, okay, as soon as you're able to see some sort of pattern, then you've got a strong relationship. Woohoo! Any questions so far? No? So just looking at these, which of the following has the strongest correlation? The correlation, sometimes we call it the correlation coefficient. And so we've got these 4 options, I almost said 3. A is a really, really strong relationship, right? But it's clearly nonlinear, right? If we tried to fit a line through here, it would go somewhere like this, and it wouldn't be able to capture hardly any of the data, right? And so fitting a straight line through here wouldn't really make sense. We'll have to either transform it or fit a nonlinear model. And so remembering that the correlation only applies to linear models, right? Because what the correlation is going to do is it's going to fit a straight line and try to figure out, okay, well, how much of that activity did I capture? Well, in this case, not that much. Right? And so here, we're going to keep going, okay, this is a linear relationship. This is a linear relationship, right? It's just weak. Here we have another linear relationship, but considering the spread of these guys and the spread of these ones, I would say that B has a slightly stronger relationship. Right here we've got a positive, here we've got a negative relationship, and so B is going to have the strongest correlation coefficient. So here, just looking at C for a sec, in here, it doesn't really matter where you're putting the line, right? You could put it like this, you could put it like this, right? And so that's what tells you that you have a weak relationship, right? When there's just kind of random scatter, a cloud of dots, and there's really no relationship. One thing about this weak relationship is that it doesn't matter what value of x you have. So with an x down here or an x up here, you're probably going to end up predicting about the same value of y, right? And so that's what makes it a weak relationship. And so I'll just circle B. Okay. So one thing that well, I took my first stats course from him, but then he was my supervisor, but he would always yell. He was a yeller. Like he would swear a lot in class, and he would always just yell, "Correlation does not imply causation." We were all like, oh, okay, got it. But it's true, correlation does not imply causation. Catchy, but also true. And he'd say it at the most random times too. It was really weird. But anyways, good guy. So just because two things are correlated, right? So a correlation, even if it's really strong, just means that there's an association between the two, right? It doesn't mean that one thing causes a change in the other. It just means that they're changing together, right? And so we talked about that ice cream example, right? So it's reasonable to assume that ice cream sales go up when the temperatures go up. So then you would have this positive relationship, and probably pretty strong too, right? But we know for logical reasons that we can't argue that, well, as long as we keep selling ice cream, just push it to the people, just sell more ice cream, the temperatures will stay high, right? Doesn't work that way, right? And so we know that logically, but when we're talking about variables that we don't know so much about, right, then it's easy to say, okay, well, this causes a change in that, right? But that's not the case necessarily, right? What's the only way we can prove causation? Causation, that takes us back to experiments, right? The only way that we can say that something causes a change in another thing is through an experiment. That was way back, but just thought I'd bring that back in. Okay? And so we have to be really careful when we're talking about correlation, right? Correlation means that, yeah, there's a relationship here, right, an association, but not necessarily a causation. Well, there can be, but just from the correlation, we can't say that. Oh, and then I'm so glad my little joke got in there. I was worried it was too far out in the margins, but I saw it printed okay, so. Phew. It's important. So, any questions about correlation? No? It's like all you need to know about correlation. And a little bit more, actually. So let's talk about fitting a line. So we're fitting a line, and so basically a line of best fit. And I remember in high school, I think it was like physics or something, where we just had a scatter plot. So we had drawn these dots on this plot, and then they're like, okay, draw the line of best fit. And you just got out your ruler and you just tried to eyeball it. It's not what we're gonna do here. But same idea, right? And so we're doing this line of best fit in order to predict new values. First, what's gonna happen is when we draw this line of best fit, a line of best fit, it's not going to go through all of the points, right? That can't happen. Okay? It's just going to be the line that minimizes the distance from each of the points. And so what we're going to end up with are these things called residuals. Okay? So the line, that's your predicted value of y. Right? So here, this line predicted value of y, or values of y. Oh, you know what? Use a smaller pen here because I'm so zoomed in. Predicted values of y. So what we do if we have to predict a value of y when x is 85, right? In theory, what we're doing is we're just going up from 85 and moving over. And that's your predicted value of y for x equal to 85. We're going to use the equation of the line to do that. But I mean, once we have our y equals mx plus b, we can plug in a value of x and it's going to spit out a predicted value of y. The predicted value of y, we denote by y hat. Confusing because we just had p hat, which was the sample proportion, right? Now the hat just means it's a predicted value. Clean up this hat. So it's going to be a matter of context. Well, a y hat is always going to be a predicted value of y. For proportions, we'll stick to p's and q's. I think that's all we do is subscripts. Okay. So it's going to be a matter of context. Okay. But so what we end up with, my line's a little crooked, are these residuals, right? So from each point, right, this point to this line at that same value of x, we're going to find these residual values. So what the formulas that we're about to use does is it minimizes the residuals in some way. And I threw it on there, the residual. I'm not going to do anything with the residuals. I'm not going to make you calculate them. I'm not going to make you do anything. But just so you know, the residuals are confusingly denoted by E because, of course, R was already taken by the correlation. And so often we call the residuals the errors, right? Because in our plot here, right, the residual is the error of our line. And so we're trying to minimize these errors. And so you've got this fancy notation here. EI, residual yi, so the I is just saying, okay, it's going to happen for each of your XY combinations or any X. Yi is your observed value of Y, right? So that's the actual Y value of your points. And then Yi hat is your predicted value of Y. Once you use the LM command in R and store it as, well, I think most of you use mod 1 because that's what I use. So often what I'm doing when I'm modeling stuff is I end up making mod 1, mod 2, mod 3, mod 4 until I find one that I like. And then I just refine that, kind of drill deeper there. But so I start out and you just fit a ton of different models, change a couple things, figure out what works, and then you go from there. But so once you've made your mod 1, right, using your LM command, then it'll have the residuals in there. So you can do mod 1 $ residuals. We obviously didn't go into that in the lab, so it's not something that I'm expecting, but just so you know, that it will just generate the residuals for you. A little fun fact is that the sum of the residuals will always be 0, right? Because some of them are positive. So if the point is above the line, you've got a positive residual. If the point is below the line, then you've got a negative residual. Once you add them all up, you will end up at 0, and that's just because of how we fit the line. But it's also just a good fact to use. Some theory behind why we use the least squares regression line. As far as you guys are concerned, no. Are you going to have to know about other or different types of regression? No. We're just going to use the least squares regression line. But two main options that we've got, right? If we're trying to minimize the distance between the line and the points, right? Minimize the residuals. What we could do is we could try to take, okay, we'll take the absolute value of these residuals, add them up, and whatever line makes that sum the smallest that it can be, right? That's the line of best fit, right? You've minimized all the residuals as best as you can. The one that we use, though, is instead of taking the absolute value, right, to get rid of the negatives, we square things instead. So that's where the least squares regression line comes from. I've got that in here. Sorry, least squares. It's all in here. And so what we do is we fit a line, right? And we try to figure out, okay, well, which one is going to minimize the square of the residuals? That's the line of best fit. And so just some reasons why we use this version instead of the absolute value version is, well, one, it's the most commonly used. It's probably the most commonly used because it's the simplest to calculate. And kind of the interesting thing is that a residual that's twice as large as another residual is usually more than twice as bad. Okay? And so by squaring it, right, you're squaring that distance and kind of amplifying the distance of that residual. Okay? Any questions? Oh. Don't worry. The first part of this chapter is all theory, but if you've had a flip through assignment 7, it's all going to be pretty manageable. Okay. So I think this is the last bit of theory we have to get in there. So remember, we've been using Greek letters for populations, right? And then just kind of normal letters for samples. And so same idea. Remember, you've got y equals, y equals, so jumpy, mx plus b, where m, right, was the slope, and b was the intercept. This is the equation of a straight line. When we're modeling, right, what we want to talk about is the whole population. So the predicted value of y for the whole population is going to depend on the population intercept beta naught and the population slope beta 1. And then x is just going to be your explanatory variable, and you're just going to plug in a value of x and solve for the predicted value of y. And so down here, or over here, I've got, okay, so some notation, right? We use betas for our m and b, right? In y equals mx plus b, we're now using betas. And And so the parameter beta naught, that's your intercept. And then the statistics that we use is just b sub 0. And then for the slope, same thing, beta 1. But the statistic that we're going to try to calculate or use our sample to calculate, bless you, is just b sub 1. Yeah.
Is the y the same if it's a sample or if it's...
Yeah. Good question. So what we will be, so our line of best fit will be y hat. Sit down and clean this up here. Y hat is beta naught or b naught, sorry, beta. I was looking at the beta, plus b1 x. And that's the one that's on your formula sheet. To calculate these, right? And so we will calculate b sub 0 and b1. We actually have to start with the slope, b1, just because to find the intercept, we need the slope. But that's something that you would just kind of arrive at by yourself if you're trying to do a problem, right? You try to start with finding the intercept, but turns out you need the slope, so then you'll find the slope and it'll be fine, right? So it's not something that you have to memorize or anything, it'll just be something that happens. So to calculate the slope of the regression line, B1, we use the correlation times the standard deviation of the y's over the standard deviation of the x's. All of those we've seen already, right? We had to have sy and sx and sxy to find r. Right? Here we've already calculated r, and we know sy and sx already. So far, we've only needed 3 pieces of information. Turns out we only need 5. We also need the mean of x and the standard deviation of, and the mean of y. Get carried away. To find the intercept. But let's talk about the slope for a little bit. So the slope, right, you're gonna have to calculate the slope. That's one of the questions on the assignment, right? But on the assignment, I've made it a little bit trickier because you have to identify the response variable y and the explanatory variable x. Notice how it's gonna matter which one is which, right? You could end up with a wonky slope if you don't have your y and your x cleared up. And so here, I'll just say order matters. Can't use sx over sy, for example. So it has to be sy over sx. Otherwise, you're going to get a wonky slope. Okay. Your slope, the slope is rise over run, right? Your slope, if you have a negative relationship, has to be negative, and it's going to get that sign from your correlation, right? Remember, your correlation is going to be negative if the relationship is negative, and so your slope will also be negative, right? And vice versa. On the assignment, I've asked you to interpret the slope, right? So find the slope is one part, interpret the slope is another part. What you're going to do is you're going to apply the definition of the slope to this particular problem. And so the definition of the slope is that for each unit increase in x, right, for every unit move over in x, we will see a slope, whatever the slope amount is, increase in the predicted value of y. I stick with increase, right? Because the slope could be negative. A negative increase is a decrease. So I don't bother throwing that in there. I don't bother thinking about it. I just say, oh, it's a -3 increase in the predicted value of y, for example. So I just stick with this same wording where you're just going to swap out your x for whatever your x is, your y for whatever your y is, and of course your slope for whatever you found the slope to be. Questions? Oh. So like I said, pretty manageable stuff in this section, which is really a nice break for you guys, I think. So the intercept, thinking back to what the intercept is is where the line crosses the y-axis, right? But it's also where x equals 0. And so we use the fact, and I think that's kind of cool, that the line of SFIT will always pass through x bar, y bar. Right? So there's going to be a point on your graph that you can find, right? You find your average of your x's and your average of the y's, and at that point, the line will pass through that point. I don't know, I think that's kind of cool. It makes sense, but it's kind of cool that it happens every time. And so we use that fact to find the intercept, because then we can say, okay, well, y bar minus, and then the slope that you just found, and then times x bar. So like I said, I need to give you 5 pieces of information, right? I need to give you the SX, SY, SXY, X bar, and Y bar. If you look back at some of those practice problems that I've posted, because I used to give the correlation SY, SX, X bar, Y bar, same idea, right? But I'll see if I have time to go back and change it, but heads up, probably not. But you can still practice with the correlation instead. So we can calculate the intercept, right, assuming that you've calculated the slope. And as far as marking goes, right, if you've calculated the wrong slope for whatever reason, I'm not going to keep docking marks. I'll follow through, right? As long as you used it correctly, you're fine. The definition of the intercept is that the intercept is the predicted value of y when x is 0. And so that's kind of the key point, is when x equals 0. So sometimes I'll follow up and say, okay, well, is it meaningful, right? Is it meaningful to know what the predicted value of y is when x is 0? And so you have to say, okay, well, is x ever going to be 0? Right? There are some cases where, yeah, x equal to 0 happens. Things like temperature, right? 0 degrees out, that can happen, right? Whereas if we're talking about if x is the square footage of a home, right, then no, you're not going to buy a house with 0 square feet. We're not talking lots here, we're just talking homes, right? And so no, that's never going to happen, and so it's not really meaningful information, right? It's just where this line would continue and then cross the y-axis. So what we said was that, okay, well, the whole point of doing these regression lines is to be able to predict new values, right? And so what we do to predict these values is we just take the value of x that we want and we plug it into the equation, right? Because now we've got our slope, we've got our intercept, and so now we can just plug in any value of x and predict the value of y. And so, of course, there's going to be uncertainty, because what you're doing is you're plugging in a value of x, you're finding that point on the line, right? And so that means that you have to figure out what the y value at that x point is, right? But because we see that there's lots of scatter around here, if we actually went out and found a point with that x value, it's not necessarily going to have the same y value. And so there's kind of uncertainty in our predictions, and it's definitely related to the correlation, right? Do you have a strong relationship where things are kind of predictable, right? Or do you have this kind of random scatter where, yeah, you can guess, but it's not necessarily going to be accurate. So what we were talking about when we said, okay, well, the intercept, right, is where the predicted value of y when x is 0. And then we said, okay, well, in some cases, yeah, x can be 0 and it's meaningful, or there's going to be some cases where it just can never be 0, and so it's not really that meaningful. When we're finding the intercept of something that's way outside of the range of the data, we're extrapolating. Okay? So when we're extrapolating in general is when we've got this range of our data here, and we're trying to use the line to predict values outside of that range. The thing is that, yeah, we've used just this data to make this line. The thing about lines is that they do continue forever and ever, right? They're straight lines and they just keep going and going and going. But what we need to keep in mind is that, okay, well, we only built this line for this range of our x's, right? And so using the line for something that's way beyond the x values that we have, that's risky business. So the intercept, a lot of the time, can be an extrapolation, making it not meaningful. Again, there are scenarios where we think, okay, well, that doesn't really make sense. Why would you do that, right? But if we've got our own data and we don't really know what it's about, right? You've been hired to analyze some data set, then it's really important to keep in mind as soon as you're extrapolating, then your estimates aren't as robust. So, for example, kind of a common one is you've got data on a child's growth between ages 3 and 8, and yeah, between 3 and 8, there's kind of steady growth, kind of a strong linear relationship, right? You're just growing, growing, growing. But because we know something about how that data behaves, right? We know that at some age, right, we're going to stop growing and kind of plateau and stay the height that we were, right? So if you tried to use this line that you made from ages 3 to 8 to predict their height when they're 25 years old, you would predict that this person's going to be 8 feet tall, right? So you wouldn't do that, right? But that's the risk when you're extrapolating just in general, right? Is that you make some sort of silly prediction like that where it's not necessarily valid. And there's lots of relationships that are strong linear relationships for some portion of the data, right? And then all of a sudden there's a plateau, or there's some curving backwards, height. No, it didn't make sense. For example, oh yeah, this image I just stole, but between the years 1900 and 1975-ish, probably, they collected data on the men's age at first marriage. Very weird thing to collect data on, but okay. And so between the 1900s and I'd say just before the 50s, there was this kind of steady decline, nice linear relationship. And then what happened here, there was kind of this upswing again. And so there's a transition area between the 50s and the 70s, where they're just kind of at an all-time low, right? And then from 1975 onwards, there's just been this upward trend again. Kind of interesting data, weird, but interesting. So if we only had this information, right, the blue dots, then yeah, you can fit a nice straight line here. You're confident in your predictions, but here's the thing, you're only confident in your predictions in this range of the years, right? Because we don't know it necessarily, but we've got this kind of weird activity afterwards, right? And so even using this line for the 50s to the 70s kind of still works, right? But if we tried to use this line from 1975 onwards, then we're in trouble, right? Because eventually we'd be predicting that, 10-year-old boys are going to be getting married. 2019, so we'd be way out here. Line would be way down here. Like before they're even born, they're going to be getting married. I guess could happen, but anyways, right? So we have to be really careful about extrapolating. Right? So, oh, I did. I had to cut it, but I had a kind of an interesting. So the BBC had published an article that said that women are going to outsprint men in the year 2156. And so it's got these two lines, and at 2156, they just cross ever so slightly, right? Because I guess if they keep increasing, or I guess, yeah, increasing their speeds, decreasing their times at the same rate that they are now, then I guess women will outsprint men in 2156. But anyone who reads that is going to say, well, that doesn't really make sense, right? So anyways, I had to cut it because it was just fluff, but anyways. Think of the paper I saved. You've already seen R squared in the lab, right? R squared is just a measure of your goodness of fit, and that's actually what it's called, goodness of fit. And so R squared is a goodness of fit measure and so R squared, we looked at the multiple R squared. There's other versions like the adjusted R squared. They're usually very similar, so it doesn't really matter. But so the R squared, it's got it in the notes, but the R squared is just the correlation squared, which means that if you have the correlation, you can just square it, and then you have R squared. Remember correlations between -1 and 1, so it's a proportion, positive or negative, essentially. So if you square it, then that value is only going to be between 0 and 1, and so R squared is a percentage. R squared is a percentage, or it's a proportion, which we can calculate, but I should be proper and say it's a proportion. Once you square a negative value, it's positive, and so if it's between -1 and 1, it just puts it between 0 and 1. Here's the thing about the R squared. How it's going to come up is kind of in a sneaky way, because I might ask you, okay, what percentage of variability in y is explained by the least squares regression line on x. And so that's a really wordy thing, but as soon as you see percentage of variability, then you know that that's going to be r squared. Whether I'm asking you to find the percentage of variability or I tell you, here's the percentage of variability. And so the key thing here is the percentage of variability. That tells you that it's r squared. So we'll have that long blurb, but as soon as you read percentage of variability, that's going to trigger and say, okay, well, that's r squared. Do I need to find r squared or am I given r squared? So if you have a nice strong relationship, because it's hinging on the correlation, it's not going to be that far from the correlation, right? If you have a high correlation, you're going to have a high r squared. And so if it's telling you, okay, well, the percentage of variability, right? So the percentage of activity essentially in your y that's captured by your least squares regression line, then the remainder of the variability is going to be due to other variables that are not included in the data. And just, well, how randomness is always with us, right? And so, but usually it's because of things that have been left out of your model, but also, yeah, things are random and there's nothing we can do. So I think we'll stop there today and then we'll go through the example on Monday. How many photocopies do I need to make for 1, 2, 3, 4, 5? 5? Got it. Got it.